Section 10.6, Application of Vectors in the Plane. Our objectives are to perform operations with linear combinations of vectors, determine the direction and angle of a vector, and to determine the resultant forces in physical applications. Let's first talk about a unit vector. A unit vector is a vector u which has a length of 1 and the same direction as a given non-zero vector v. So u would be the scalar multiplication of v, and the way that you would find that is just by multiplying the vector by 1 over the length of what the vector is, or the magnitude. For example, we want to find the unit vector u with the same direction as a vector of v. So remember, if you recall, this is the component form of the vector. So if that is the component form, then if I want to find the unit vector, I need to find the magnitude of this vector v first. So that's the first thing I would do. So the magnitude, remember, is just your Pythagorean theorem. So if this is component form, that means my horizontal component is 3, my vertical component is 4, so 3 squared plus 4 squared, and take the square root of that. That would give you the square root of 25, which is equal to 5. So I know that the magnitude, or the length of vector v, is 5. So to find the unit vector u, then I would divide my horizontal and vertical component both by 5. So then u is going to be equal to 5, or not 5, sorry, 1/5, because it's 1 over the length. So 1/5 times 3 comma 4, which is equal to 3/5 comma 4/5. So this right here would be my unit vector. Now we have standard unit vectors. Standard unit vectors are the vectors 1, 0, and 0, 1, which represent the horizontal and vertical components denoted by I and j. These standard unit vectors can be used to represent any vector that we have. Now, this is just kind of like component form, but it's just another form that we have. So I does not mean imaginary when we're talking about vectors, so don't get confused. But this would be I, and this would be j. So j is always the vertical component, I is always the horizontal component. So if we look at the problem that we just did above, if I wanted to write this, and this is actually called the linear combination form. So if I wanted to write the linear combination for that vector, I would write 3i plus 4j. That would be written, vector v written as a linear combination. If I wanted to write the unit vector that I found as a linear combination, this would be written as 3/5 I plus 4/5 j. And again, it's just another way of writing vectors out, which are sometimes more useful when we're doing linear algebra and in physics. So again, it's just another form. And for this one, then our vector sum ended up being, for my linear combination, vector v1 of I plus v2 of j would end up being the linear combination. So it's your horizontal component I plus your vertical component and j. Now if we want to find the linear combination of vector v, given the initial point is at -6, 4, and the terminal point is at 0, 1. So -6, 4 is the initial point. This is my terminal point, so that would be my line right there. And if I want to find the linear combination, then I need to find my horizontal and vertical distance. So I can actually just count on here. I know that this distance and this distance are the two distances that I'm looking for. And remember, we can also do this in component form and then rewrite it in as a linear combination. So that's what I'm going to do first. So vector v would, in component form, remember, you subtract your terminal point x minus your initial point x and then the y's. So 0 minus -6, comma 1 minus 4, which ends up giving me 6, comma -3. And if we look at our graph just to confirm this, if you go from here 1, 2, 3, 4, 5, 6 in the negative direction and up a positive, and actually, sorry, we went down first 3, so it's down 3 because our vector is going the opposite direction this way. So that's why it's -3. So to get to the terminal point, we had to go down and then to the right 6. So for this is my component form, but I want to write this as a linear combination. So then as a linear combination, it would just be 6 I plus, or actually minus, because it's negative 3, so minus 3j. So that would be written in linear combination form. Again, it's just the same thing we've been doing, just a different form. The next one says find the component form of v equals 2u minus 2w, given that u is equal to 2i minus j and w is equal to I plus 2j. So if it says to find the component form, then I would probably want to write vector u in component form. So this would just be 2 comma negative 1, and vector w in component form would just be 1 comma 2. Again, pretty easy to write that in the other forms. So now we're doing vector v, which is equal to 2u minus 2w. So I'm going to do 2 times each of these first. So 2u would be equal to 2 times this. So this is really equal to 4 and negative 2. And 2w would be equal to 2 times this, which gives me 2 comma 4. And then the last step would be to subtract those two, and remember the order in which you subtract does matter. So for vector v, it would be equal to, we're taking u minus w, so 2u minus this, so we have 4 minus 2, comma, negative 2 minus 4, and I'm going to extend that a little bit, so then we end up with the new vector v being equal to 2 comma negative 6. So that would be my new vector. If I wanted to write this as a linear combination, then I would write 2i minus 6j. So this would be linear combination. Okay. Now, position vector is a vector with its tail lying at the origin, which is 0, 0. The components of the direction angle, if we have vector v, the components a and b, which is also written as linear combination as ai plus bj, then we can state that we can find our we can find a and b if we know the length and we know the component forms of our vector. So just to show you, let's say that we had our vector here. So if this is our vector, which we're going to call vector A and B, we're going to use the component form. So for this vector, which we're going to call vector V, I know that this distance right here is a distance of A, and this distance right here is B. The direction of this angle would be right here, which is theta. So if I know what the angle is and I know what the length of the vector is, I can find my horizontal and vertical components A and B. The way that I do that is by using right triangle trigonometry. So if you look here, if I did the sine of theta is equal to opposite over, and let's do the length of V, hypotenuse, or the magnitude. So then B would be equal to the length or magnitude of the vector times the sine of the given angle. And then if I wanted to find A, I could do the same thing, except for A, I'm doing the adjacent over hypotenuse, which is the cosine of the angle is equal to A over the magnitude of the vector. So A would be equal to the magnitude of the vector times the cosine of theta. So these are two more formulas that we have. So that would be given the magnitude and also given the direction of the angle, we can find the components A and B by using these two formulas. Notice that A is using cosine for the horizontal distance, which makes sense because remember we said before using our unit circle that cosine was the x-coordinate, sine was the y, so it makes sense that the B, which is the vertical component, then would be the magnitude times the sine of the given angle. Now, the direction angle is the angle theta that represents the direction of the vector in the plane from the positive x-axis to the vector. Any point in the circle can be represented by cosine theta, comma, sine theta, which we talked about with the unit circle. So we can represent any vector as cosine theta, comma, sine theta, cosine theta I plus sine theta j would be the linear combination form. So to find the direction angle, we can use the tangent. If we know what the magnitude and the sine is, and also the cosine, to find the tangent, you can just divide those two, because remember, tangent of theta is equal to sine theta over cosine theta. So in this case, if you know what A and B are in component form, then you can divide A and B, because remember, this is really vector magnitude v times the sine of theta is really equal to your b over the a. So if you were to do the tangent inverse of b over a, you can get what your angle of theta is equal to. So we'll do some practice of that. Now the next one says find the magnitude and the direction of angle of vector v, which is 12i plus 15j. I usually like to work in component form, so I'm going to go ahead and just rewrite this. So I'm going to write this as 12, comma 15. Now, if I want to figure out what the magnitude is, or the length, so the magnitude of vector v, if we have the horizontal and vertical components, remember we can just do the Pythagorean theorem, so take the square root of those both squared and added together. So when I do that, I end up with the square root of 369, which ends up giving me, when I reduce it, 3 times the square root of 41. So this is, again, the magnitude, or the length, of the vector. Now I need to figure out the direction. So the direction is going to be the tangent if we know the components a and b. So the tangent of theta is equal to, remember we said sine over cosine, so b over your a, which is your y over your x. And then to find theta, theta is equal to the tangent inverse of 15 over 12. And then you can use your calculator and plug this into your calculator and make sure you're in degree mode when we're talking about vectors, not radian mode. So in degree mode, the direction would be equal to 51.3 degrees. Now, when you're doing this, remember we talked about doing the inverses of tangent, and when you do the tangent inverse, you're getting solutions in quadrant 1 or in quadrant 4. So you have to be very careful to also think about what your vector would look like if you were to put it on a coordinate plane. So if I'm going 12 and then 15, so 12 horizontally, which is positive 12, and positive 15, that means that my vector is going something like this. So it makes sense that the direction angle would be 51.3 degrees. If it was in one of the other quadrants, then you have to be careful to make sure you either add or subtract some different values to get what the angle might be if it's in quadrant 3, because remember, again, tangent inverse, you're only finding answers in quadrant 1 and 4. So you have to be careful, and we'll do some of that a little bit later. So the next one says, find the component form of vector v, given that the magnitude of v is 3, and v is in the direction of 3i plus 4j. So if this is the direction, that can help me figure out what the angle is going to be. So in order to figure out the angle, I'm going to do the tangent of inverse. So theta, the tangent of theta is equal to 4/3, so theta is equal to the tangent inverse of 4/3, which is equal to, I believe what we just had in the last one, close to it, so 53.1 degrees. So that would be theta. And then I need to figure out what my components are for this. So the components, you define them. Remember, you take your magnitude times your sine of your angle, and then your magnitude times the cosine of your angle. So for this one, we're going to do 3 times the cosine of 53.1 degrees, comma, 3 times the sine, because sine is y, of 53.1 degrees. And then all I have to do is multiply all this out. So when I do all that, I end up with 1.8 comma 2.4. And that would be my component form for vector v, given that the magnitude is 3 and the direction is 53.1 degrees. So then for the next one, it says find the component form of u. So for the component form for this one, if we're given the magnitude and the angle, it's easy to find. So the component form would be 35 times the cosine of 25 degrees, comma, 35 times the sine of 25 degrees, and then all you have to do is plug that into your calculator. Again, make sure your calculator is in degree mode, otherwise you'll get these answers incorrect. So when you do that, you get 31.7, comma, 14.87, and of course you can always think to make sure this makes sense. We're going to the right 31.7, so horizontal distance, and then a vertical distance of 14, which makes sense if the direction angle is at 25 degrees. All right, so let's do some application of these problems. Find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at the angle of 30 degrees below the horizontal. So the picture that you have to the right is what shows us what it should look like. We know that this length or magnitude of the vector would be 100 because it's going at 100 miles per hour, and we're at 30 degrees below the horizontal, which would be this right here. So they give you the fact that if that's 30, then from here to here would be 210 degrees. So that tells me that theta is equal to 210 degrees, and we know that the magnitude is equal to 100 because it's 100 miles per hour. And so if I want to find the component form, then we just use our formula. So you take your magnitude, and then your x would be the cosine of 210 degrees, comma, your magnitude times the sine of 210 degrees. And when I plug this into my calculator, I get negative 86.6, comma, negative 50. For my horizontal and vertical components. And then if I look at my picture, that makes sense because I am in quadrant 3, so I have a negative x and a negative y. Now, let's recall that the resultant force is the sum of all the forces acting on an object. And remember that the resultant force is just when you're adding your forces together. So an object at the origin is acted upon by two forces. A 150-pound force makes an angle of 20 degrees with a positive x-axis, and the other force, 100 pounds, makes a 70-degree angle with the positive x-axis as shown below. We want to find the direction and the magnitude of the resultant force. So for this one, we have our first vector right here, and that one's making the 70-degree angle with the positive x-axis. This one is our other vector, which is making a 20 degrees with a positive x-axis. And if we want to find the resultant force, it's the sum of all the forces acting on the object. So when we add, you do the parallel, the sum, head to tails sum. So if I moved this vector OP to here, that means that the resultant force is going to be this vector right here when we add them together. So all we have to do is add the two. So in order to do that, then I need to first figure out what the component form is for vector OQ and OP. So let's do OP first. OP would be equal to, so we have the angle, and we also have what the magnitude is. So 150-pound force is what it tells us makes a 20-degree angle, so 150 times the cosine of 20 degrees, comma 150 times the sine of 20 degrees. And if we do the other vector, OQ, that is going to be equal to, what was it, 100 pounds? So 100 times the cosine of 70 degrees, and 100 times the sine of 70 degrees. And so basically what we're doing to find OR, which is the resultant force, we are going to add these together. So we're going to do OP plus OQ. And you can, of course, just plug this into your calculator to do that. So for this one, we're going to do 150 cosine 20 degrees plus 100 times the cosine of 70 degrees. And then the y-coordinate would be 150 times the sine of 20 degrees plus 100 times the sine of 70 degrees. And in your calculator, just make sure you are in degree mode when you're doing this. So when I plug it in for the first x, I get, or the horizontal component, I get 175.16. For the vertical component, 145.27. So that's what I'm going to put here. So I have 175.16, comma 145.27. I'm not done because the question says we want to find the direction and magnitude of the resultant force. So I have the components of the resultant force. Now I need to find the magnitude. So if you recall, the magnitude is just using your Pythagorean theorem. So the magnitude of OR would be equal to the square root of 175.16 squared plus 145.27 squared. And when you end up doing that, you end up with the magnitude being equal to 227.56. So this is the magnitude. And of course, we're talking about pounds, so 227.56 pounds. And then we want to find the direction. So to find the direction, remember you just take your new components and you're going to take your the tangent of dividing the y over the x coordinate. So the tangent of theta would be equal to 145.27 divided by 175.16, and then do the tangent inverse of that, and you end up with theta being equal to 39.67 degrees. So the direction would be 39.67 degrees, and the magnitude is 227.56. All right, so one last problem. So I'm going to make that smaller. Okay, so I just made it a little bit small and rewrote it. So let's do the last one. So for the last one, an airplane is flying in the direction of 75 degrees with an airspeed of 210 miles per hour. A wind of 50 miles per hour is blowing from the direction of 150 degrees. We want to find the course and the ground speed of the plane. So I'm going to actually copy this onto a new page so I have more room to work. Okay. So the first thing I like to do is I'm going to draw a picture so I can kind of get an idea of what this looks like. So an airplane is flying in the direction of 75 degrees with a speed of 210 miles per hour. Now, navigation direction is different than how we are used to from our unit circle, drawing out our angles and measurements. We normally started with this with 0 degrees, and this is 90 degrees. However, when you're talking about navigation, north stands for 0 degrees, and then east would be 90 degrees. South gives me 180 degrees, and this is going to be 270 degrees. So it's a little bit different. So if I'm flying in the direction of 75 degrees, that means that from here to here would be 75 degrees, and the speed, which gives me my magnitude, would be 210 miles per hour. So this is for the plane. And then the wind is a little bit different. So the wind, let's take a look at that. You have to be careful when you're doing the wind to see, read the problem to make sure that you're not coming from the wrong direction. So the wind of 50 miles per hour is blowing from, the key word, the direction of 150 degrees. So if it's coming from 150 degrees, you're going to be blowing in the direction. So you kind of have to do the opposite of what you think it would be. If you think about 150 degrees in navigation, 150 degrees would be somewhere over here because you would be going from here to here. But the problem is that it says the wind is blowing from the direction of 150 degrees. So that means instead of my arrow going that way, I'm really going this way. So I need to have my wind arrow up there. And now the problem is I have to figure out what the distance is going to be all the way to this side. Now, when we're doing these problems, we can't use navigation for our sine and cosine. We have to use what we've learned previously, like this is the 0 degrees. So instead of using 75 degrees for this plane, I'm going to use 15 degrees because 90 minus 75 is 15. So that would be using our unit circle measurements that we've learned. If I look over at this wind, then for the wind, we're going to be going from here to here. So I know I have 90 degrees, and this little measurement from here to here is 30, which means that this is 30. So if I have 90 plus 30, I know that this from here to here is going to give me 120 degrees, which is the angle that I'm going to be using. So if I want to find the course and the ground speed of the plane, that means I want to find the resultant force, which is going to be the plane. So I'm going to call this P, vector P, and this vector W for plane and wind. So vector P plus vector W would be the help you find the course and the ground speed of the plane. So the first thing I need to do is figure out the components for the plane. So the components for the plane would be, and I have the angle and I have the magnitude. So the horizontal components, remember, are going to be your magnitude times the cosine of the angle, and then the magnitude times the sine of the angle. And again, remember, you're in degrees. So the plane components are 202.8444 and 54.3519. Then if I do the wind, so let's use blue for wind. The wind components are going to be, and we said it was blowing at, what did we say, 50 miles per hour? So that's the magnitude. So 50 times the cosine of 120 degrees, and then 50 times the sine of 120 degrees. So when I find the components for the wind, we have -25 and 43.30137. So now that I have the components for the plane and the wind, the resultant force would then be to add those two together to figure out where your plane actually is. So if I add these two together, then vector P plus vector W is equal to 202.8444 plus actually minus 25 because it's -25. So minus 25, comma, and then the y coordinates would be 54.3519, comma, 43, so plus, not comma, sorry, plus 43.30137. And if I add those together, I end up with 177.8444, comma, 97.6532. So that's the plane, horizontal and vertical components. Now, if I want to find the magnitude, so this was this right here, so the magnitude of P plus W, you add those two together and take the square root of your answer. So if we add this and then take the square root of that, we end up with 202.89. So miles per hour would be the speed. And then if I want to figure out the direction, I take the tangent of my y-coordinate divided by my x-coordinate. So the tangent of theta is equal to 97.6532 divided by 177.8444. The tangent inverse of this would give me theta being equal to, make sure you're in degrees, 61.23 degrees. Now, the problem, oh, sorry, that's the wrong one. So theta is equal to 28.77 degrees. Now the problem with this is that's not the direction, because the direction needs to be in terms of navigation. So we need to put this in so it's 28.77 degrees. Then to figure out the navigation, because remember this is 0 degrees of navigation, so 28.77, what we're used to would be right here. But we need to figure out in navigation it would be from here to here. So how do I figure that out? I can take 90 degrees minus 28.77 degrees to get the direction angle of theta, which in this case would be equal to 61.23 degrees. So that means that the direction is right here, and the magnitude would be 202.89 miles per hour. So that actually is the speed and the direction of the plane. If we have a wind that is blowing 50 miles per hour from the direction of 150 degrees. So we're going to do some practice of these because it can be a little bit tricky because you have to think about this in terms of navigation. But these are the types of problems that we will be